Все,
О,
ура.
все, тогда можно ничего не делать, Сергей Константинович, и просто
Хорошо, тогда, значит,
расслабиться и начать слушать.
сосредоточиться и начать слушать.
Сосредоточиться.
Хорошо, тогда, Антон, прошу.
So thanks for the invitation. I have to apologize in advance because somehow it was difficult to prepare this lecture. It was difficult to concentrate. And I can just say that I always disliked politicians and generals of all countries. Now I just hate them. And I could never imagine that the movie of Kubrick on Dr. Strangelove would one day would seem just a pale documentary compared to absolute craziness of reality. But somehow to hide from reality, I suggest to concentrate on mathematics. And I would like to, today I would like to speak about meanders and to explain how count of square tiled surfaces help in counting meanders, at least in some setting. And that's the subject. So, and first, reminder of what is meander. So a closed meander is just a simple closed curve in the plane transversely intersecting the horizontal line. And according to Serge Landau and Sasha Zvonkin, the notion of meander was suggested by Vladimir Arnauld. The two meanders were studied already by Henri Poincaré, and actually they appear in various contexts, in particular, not only in mathematics, but also in physics and biology. So the conjecture, which Serежа, I apologize, for quite a while I was erroneously attributed it to Di Francesco Gulinelli and of apparently Landau and Zvonkin is that
Я прошу прощения, Владимир Стукачев, отключите, пожалуйста, звук.
Да.
Спасибо вам. Sorry, Anton.
It's okay. So that the number of meanders with two end crossings is asymptotic to the number which you see on the screen. I should specify that in this particular setting, the conjecture was specified by Di Francesco Gulinelli and Gutier in '97, who suggested a conjectural exact value of alpha, and the value of r squared is also conjectural and only approximate. So their lower and upper bounds for the growth number of meanders, but both bounds are unfortunately at the current stage very far from the desired one. So this is null conjecture. And now what can we do with meanders? How can we approach the problem of counting meanders? Well, we can count a meander along this red line, and then we get a system of arcs in the plane. We can also compactify the plane, and then the plane will become sphere. The red horizontal line will become the equator of the sphere, and the collection of arcs would become collection of arcs on southern and northern hemispheres. So it will be a collection of arcs in a disk, and we'll use the following combinatorial passport of system of arcs. So that's the picture of a meander in the plane, and the combinatorial passport would be the following tree. We can construct a dual graph to collection of arcs, and this would be, since we live in a disk, so this dual tree is drawn in black. So we have two, this Mercedes sign on top and this Mercedes sign on the bottom. And when meander is complicated, we usually have plenty of vertices of valency 2. So combinatorial passport corresponds to forgetting these vertices of valence 2, which are sort of not very interesting, and memorizing only the structure of the tree with this vertices of valency 2 forgotten. So one can...
sorry, you mean
yes?
A meander is complicated or an arc system is complicated?
When the meander has a lot of intersections, well, sort of here the meander is very short. So when meander is complicated, then usually you have plenty of vertices. You might have plenty of vertices of valency 2. I suggest to forget about that. Just
yeah, but I'm asking about what you are precisely speaking about, a meander or an arc system?
I'm giving a definition of combinatorial passport. I'm saying that combinatorial passport of a meander, this is a pair of trees which are obtained in the following way. So I take these two arc systems, and for each of the arc systems, I take the dual tree, so dual graph, but in our particular case, this graph is automatically a tree. And then I sort of impose to forget the vertices of valency 2. This is construction, a definition. So the resulting pair of trees I call the combinatorial passport. So in this particular case, the combinatorial passport would be just two pure Mercedes sign trees, one vertex of valency 3 and 3 leaves, 3 vertices of valency 1. So the observation is that actually it is easy to compute arc systems. There is just explicit formula. But the trouble is that when we try to reglue a meander from two arc systems, sometimes we do get a meander, like on the left picture, and sometimes we do not, as on the right picture. So in both cases, so this is just a tennis ball. And if I cut this tennis ball along the equator, depending on the angle which I use to twist the tennis ball and to join the ends of the corresponding blue line, the ends of the corresponding pair of arc systems. So sometimes I get a single connected blue line, like on the left picture, which is meander, which is exactly what we want to get. And sometimes I will get a blue multi-curve on the right picture. So in a sense, if we would know how often we get meanders gluing a pair of arc systems, what is the frequency of meanders out of all curves, we would solve the problem in a sense. So I suggest to formalize it. So let's count this frequency of meanders out of random gluing of pair of arc systems, but now I have to define what kind of pairs of arc systems I consider. I suggest to change the setting, and I change the initial problem of just count of all meanders with at most certain number of crossings. So I replace the problem by sort of adjacent one. Namely, I fix the combinatorial passport. Let us fix the combinatorial passport, the tree on top and on the bottom, and then consider arc systems which correspond to this fixed combinatorial passport, to which we now start adding these vertices of valency 2. So in my particular case, with this Mercedes sign arcs combinatorial passports, what I do, and I forgot to say, and then we always keep the same number of arcs on the right and on the left, and we consider all possible ways to turn the equator, and then we glue them and we count how often we get meanders. So we made all possible turns, we counted how many meanders we got out of these gluings, and now we add new arcs, keeping the same combinatorial passport. And then we add new arcs, and we do the same. We make this, now when we have this large number of arcs, we consider all possible turns. So they would be, if they are n arcs, they would be 2n twists which one can use to glue together these two pairs of arc systems. Sometimes we'll get a single simple closed blue curve. Sometimes we'll get a multi-curve. And let's count how often we get a meander if we consider all possible arc systems with corresponding combinatorial passports when the number of arcs, with bounded number of arcs, when the number tends to infinity. So we look among specific arc systems with these passports, what is the frequency of meanders out of all possible gluings of arc systems? And here's the theorem. The theorem says that actually the answer actually depends on the number of leaves, or the total number of leaves. So for passports like this, two Mercedes signs, we have 3 leaves for each graph, for each tree. So in total, there are 6. For this pair of trees, we also have 6 leaves, 6 vertices of valency 1. And for both passports, the probability to get a meander gluing a random arc system with this kind of passports is indicated here. It's approximately 1/3, which is not small at all, which I don't know. So, and here is exact formula for any p. So for p equal to 6, we get this number. And so it's, in particular, it's very far from 0. The probability is always non-zero. And in this particular case, it's really high. It's about 1/3. And as I already mentioned, this allows to count meanders in the following setting. If we
Anton, did you expect that the probability will always be non-zero?
So the question is,
when you were starting thinking about the problem?
No. I should say that naively, I thought that it would tend to 0 because you have just this enormous amount of arcs, really many of them. And with a probability 1/3, you get just one single curve which goes and goes and goes around this sphere, comes and goes down, comes back. To my mind, this is, for me, it was sort of counterintuitive.
That's why I am asking.
For me personally, it was counterintuitive. Maybe for somebody more experienced with this kind of problems, it would be, I don't know. What about you? Does this answer seems, so you work with meanders for what, for already 30 years? Does it seem to be to you counterintuitive, or sort of?
I would not say I spent enough time in thinking about this specific setting.
We can ask Sasha Zvonkin, and I use this opportunity to make publicity for his recent survey on meanders, which is great as everything which Sasha writes, and which somehow describes their current state with meanders. It appeared about two or 3 months ago.
It appeared earlier, probably a year ago. At least I have seen
but
more or less
publicly
final version. I don't know. Maybe.
Okay.
Yeah. Sorry.
So now since we know how to count probability, that I already mentioned that it's a simple problem to count arc systems. And now when we know the probability to get a meander out of a random pair of arc systems, it's not surprising that one can count meanders in the following setting. So what was the leaves of combinatorial passport correspond to this black minimal arcs. In some papers, they're called pimples. So if you fix the number of these black pimples, then the previous formula instantly give you a formula for the number of meanders. You have to distinguish between meanders, closed meanders of the type as on the right and as on the left, because what really counts is what happens on the sphere after compactification. And on the sphere, this rainbow, the arc which joins the leftmost point with the rightmost point, which appears for some meanders. Actually, on the sphere, it becomes one more pimple. So these are the formulas for the number of ones and the number of the others. They're quite explicit. And Maxim, I apologize, I will first tell the results, and only then there would be some proofs and some demystification of what is going on. I just want to add that we can define analog of meanders on surfaces of any genus. So we can define pairs of transversally intersecting simple closed multi-curves on the surface, and to say that a meander, this is the situation when we have just one blue simple closed curve and one red simple closed curve transversely intersecting it. And on surfaces of high genera, one can also define oriented meanders. So as one can define oriented pairs of multi-curves. So we have to orient every connected component, and we have to request that all intersections are positive. And we can say that a pair of multi-curves is orientable if it admits an orientation. So you can check as an exercise that the pair of transverse multi-curves on the right is really positively intersecting, and that the pair of multi-curves on the left is non-orientable. You cannot orient components in such a way that this orientation would be consistent, and so that all intersections would be positive. So I will explain shortly why we count oriented or orientable meanders separately. And now,
and if you have just genuine meander, so that there is one blue and one red component, it also could be non-orientable.
It can be non-orientable, absolutely. It's sufficient, for example, to have a pimple. So if you have a loop, so it crosses and then instantly, without having anything inside. So then it's non-orientable because one crossing is positive and the other crossing is negative.
I see.
So let me first formulate results on in the case, in non-orientable case. So let's fix the genus of the surface. And in this case, we have to fix, as before, a non-negative integer denoting the number of bigons produced by intersections of pairs of multi-curves. So the observation, which I will justify shortly and which would be related to count of square tile surfaces, which appeared in the previous lecture, is the following. So we can count the following three numbers: the number of pairs of transverse multi-curves with at most n intersections and with exactly p bigons, and the number of pairs of transverse multi-curves like this grows polynomially. The power of n, which is the number of intersections, is 6g minus 6 plus 2p. And there is some non-zero coefficient here, which depends on g and p. Now we can count the subset of the previous set. Now I require that, say, the red curve is simple closed curve. It's not multi-curve anymore. It's just single simple closed curve. And the blue curve is some transverse multi-curve. We get subset of what we had before. And the claim is that we have the polynomial growth of number of pairs like this, where I can see the pair as before as meander up to homotopy and up to free homotopy. So, and there is another non-zero coefficient here. And finally, the last number is we pass to subset even of the previous one. So we have three nested decreasing subsets. And the last subset is the smallest one. This time, I assume that both multi-curves are just simple closed curves, red one and blue one. So this is the meander case. And the statement is that in this case, the growth number of pairs like this is still polynomial with the same power of n with some third coefficient. And the way we can count meanders is based on the following theory. So these three coefficients satisfy the relation which you have at the bottom of the slide. So you take two consecutive nested subsets. So here, this coefficient is responsible for single closed red curve, no restrictions on blue curve, and in denominator, no restrictions on red, no restrictions on blue. So we take the ratio, it is smaller than 1, or at most 1, because the numerator is responsible for the subset. And on the right, we take single closed red curve, single closed blue curve in numerator, and single closed red curve and no restrictions on blue in denominator. We get the ratio, we get one more number, which is at most 1. And the claim is that two ratios are the same. You can see it as equality of probabilities. And I will reinterpret this as equality of probabilities shortly. So what you have on the left can be interpreted as you take by random a pair of transverse multicurves, and you count how often, what is the probability to get a multicurve where the red one, the horizontal one, is simple closed. You count this probability. So this is the frequency of those where the red one is just simple closed curve. Now on the right, you have the conditional probability. Suppose that you already know that the blue multicurve is a simple closed curve, and you have not about red one. You take one by random. What is the probability that red one would be also simple closed? And the statement is that this conditional probability is the same as the non-conditional probability in this interpretation. Now, to finish the statement of results, several facts about the arithmetic properties of these constants. So the constant C, which depends on the genus and on the number of...
Sorry, may you return to the previous slide? Yeah. Do we know that, for example, in the first row, number of pairs of transverse multicurves with at most 10 intersections is a polynomial in N?
I'm almost sure it is not. So it's only a asymptotic formula, and you never know. The objects here are extremely, well, there are so many rich geometric structures that you never know. It it might be some tricky quasi-polynomial, but I doubt that it's even quasi-polynomial. I think that it's just, I think that this is just a asymptotic relation. And I suspect that when n, wait a bit. We have sort of, so we have experiments which show that it is not polynomial. The experiments cannot exclude that it is some tricky quasi-polynomial. But I doubt it, and I think that we can enhance the experiments and prove that it is not quasi-polynomial. I think that morally the prime decomposition of n can be very influential.
Okay, sir.
Asymptotic formula. I'm afraid that it cannot be improved to anything better than this asymptotic formula when n tends to infinity.
Mm-hmm.
Anton, well, yeah. This C1 is the condition is a simple closed curve and at most n intersection and exactly p begons, or at most p begons.
Exactly p.
Mm-hmm. Okay.
At most n intersections and exactly p. Mm-hmm. Jumping ahead, these constants are related to Мэйзура-Вича volume of the moduli space of quadratic differentials of in genus G with p poles. So it's so the tangent space to MGP, cotangent.
Okay. Mm-hmm.
So I already made the confession, so it is sort of, I'm spoiling the pleasure to recognize Мэйзура-Вича volumes in all these guys. But so this constant, it's really Мэйzura-Вича volume. So its arithmetic structure is a rational number times pi power 6g minus 6 plus 2n. Now this C1 and is just a rational number, and C11 is also a rational number. Now, how efficient is this? For small p and for g, say up to 500, thanks to recursion of, well, there is a formula for Мэйзура-Вича volume due to Chen-Muller-Sauvaget, which expresses it in a very particular Hodge integrals, where there is also tau2 to some power involved. And Maxim Kazaryan and independently Yang, Zagir, and Zhang wrote recursions for these Hodge integrals, and you can very efficiently compute these things, you see, up to genus 500. P is not supposed to be too large, but with respect to G, the recursion works perfectly well. You can compute these numbers explicitly. Now, when genus is more than 500, you can apply asymptotic formula for the Мэйзура-Вича volume, which is very recently proved by Agarwal. So it's our conjecture, which was proved by Agarwal. And now this one, number C1, is expressible only in Witten-Concevic correlators of where n is either 1, for which we have explicit formula, or 2, for which, together with Gужар, Делекруа, and Zogраф, we proved very short asymptotics. So as a result, we know perfectly well this numerator and denominator, and we can compute C11 explicitly for G up to 500 and approximately with very good approximation for G larger than 500 when needed. Now, the regime when we cannot do much is when P is this number well, this number is sort of comparable to G. Here, we do not have any results yet, or even when it's larger, even less. Okay, so, and as a matter of fact, so now I can go backwards. We can do the same story as in genus 0 and relate the corresponding results with a probability to identify two boundaries of a surface where we have same number of components of branes on each boundary component, and to count the probability how often we get a simple closed curve after such an identification. So the probability is this C1 GP divided by C GP. And once again, it depends only on the, it does not depend on the way we divide the surface into pieces. So it depends on genus and on the number P. Now, yeah, sorry, I moved in the wrong direction. In orientable case, everything is completely analogous, just literally analogous, except that the power of n is much lower. It's 4g minus 3. And this is the dimension of the principal stratum of abelian differentials. But otherwise, everything is closely related, except that now to compute these numbers, so we use this formula to compute oriented meanders, and we have to compute denominator and numerator. Denominator is Мэйзура-Вича volume of principal stratum of abelian differentials. And once again, there is a recent recursion due to Chen, Möller, Sauvaget, and Zagir. For any reasonable G, say up to G 2000, you can compute these numbers explicitly. And for large genus, you have asymptotic expansion of asymptotic formula with expansion in negative powers of G, so we can get very good approximate value. Now for C1, in a sense, the problem can be reduced to a problem which was solved by Zagir on counting the number of long cycles such that their product, I mean permutations of an element, a single long cycle, and a count of how many of them live in the given has imposed decomposition into cycles, where you have certain number of non-trivial cycles and complete with arbitrary number of cycles of length 1. And I will arrive at this shortly. And again, there is the uniform upper and lower bounds, which in large genus becomes very good. And for particular, and in this particular case, we have explicit formula for C1. And again, you can compute the probability this time, since we want to get oriented system of multi-curves. All these branes have to go from one boundary component to another. And you have a surface of certain genus with two boundary components. And you have sort of a braid like this. You identify two boundary components, identifying the ends. And you can ask, what is the probability to get a simple closed curve? So now there is no this second parameter. There are no bigones. They are forbidden because we were in oriented case, so the only parameter is genus. And the answer is particularly simple. So you get a simple closed curve with probability 1/4G. So I dream to go to a store which all kind of equipment for dancing clubs and whatever and to construct something with, how do you call it, their optical fibers, where I can put a laser and see how many components do we have to somehow to illustrate it in practice. You had a question.
Anton,
Mhm.
how were the colors chosen in this situation
Randomly.
for the segments?
They have strictly no significance. Oh, sorry. No. I apologize. The picture was done. I made this picture like 3 years ago. I forgot. They correspond to sort of interval exchange transformation. So you see these 3 red guys, they are sort of parallel to each other. And so I can say it differently. So the circle on the left can be splitted into 4 intervals so that their discrete map which we get is an interval exchange transformation of 4 intervals. So all these 3 red curves, they appear consecutively on the left and they appear consecutively on the right. Then the 2 blue curves, they appear here before red, there they appear after red. Then there is single green, and then there are 3 consecutive purple, which appear as 3 consecutive purple here. So it is.
I see, and we may assume that the lengths of the intervals are proportional to the number of.
Yes, exactly. So we have circles of integer length, and we consider integer circle exchange transformation. Well, interval exchange transformation of a circle. Yes, it is just geometric topological illustration of interval exchange transformation, and this is, by the way, this is sort of the geometric picture of Arnold's problem, asking how often we have a single trajectory. So that's the answers, and now finally I can pass to ideas and then to proofs. So I recall that that's the square tiled surfaces which I was counting in the first 2 lectures, and that we can associate a quadratic differential to any square tiled surface, because we can declare that horizontal side is real coordinate, vertical is imaginary coordinate, and then we have coordinate dz on such surface, and the form dz squared is well defined not only on the part but on the entire surface. And now the relation to meanders. So I will first relate square tiled surfaces to pairs of multi-curves. When I have a square tiled surface, I can draw a red multi-curve in the following way. I take a horizontal curve passing through the center of any square. By construction, it would close up. So I get certain collection of red curves. And I can also consider a vertical curve passing through the center of every square. And I get a collection of blue curves, and together they intersect transversely. Now, if I forget about the flat structure, I just get a pair of multi-curves on a sphere. And that's the way, and in genus 0, this is bijection. So having a pair of transverse multi-curves on the right, I can reconstruct a square tiled surface. Now, since I'm speaking about all genera simultaneously, I have to confess that on high genera, this is not a bijection anymore. But it is not a bijection on a collection of objects which cardinality is negligibly small compared to all objects. So it's almost bijection. It's sort of asymptotic bijection. Asymptotically, it is bijection. We can neglect the difference. For genus 0, it is just honest bijection. And now you can recognize my quantities. So, oops, sorry. I have to. So this is a reminder of what is Мэйзура-Вича volume, and a brief reminder of what is Мэйзуra-Вича volume. So since my moduli spaces, for example, abelian differentials are modeled on this first cohomology with complex coefficients, I use this integer lattice inside to define the volume element. And I also use this quadratic function on homology to define, so it's positive function on our space. And I can disintegrate, so I can either consider square tile surface, well, all objects here which correspond to area 1, or I can consider a cone of where the area is at most 1. So it is, they give analogs of unit sphere and unit ball, and the theorem of Мэйзура-Вича is that the total volume of any stratum is finite. Now, my points of the lattice which I used. So a point in the lattice, in this cohomology lattice, geometrically it is exactly a square tile surface. For example, for abelian differential, it's particularly visible. So if we have a point of our moduli space, which in our period coordinates represented by a point of the lattice z plus iz, then I claim that the corresponding flat surface is a ramified cover over torus with a ramification over a single point. And the proof is by construction. I construct a map from my surface to the torus, where torus is complex plane quotient over z plus iz. And the map is as follows. I fix some 0 of my holomorphic point form. And then I send a point P to the following complex number, computed modulo z plus iz. I join my fixed point, which is fixed one and forever. This is one of the zeros, to my point P, which I want to send to the torus, and then compute integral over the path joining P1, which is fixed to my moving point P. I compute integral of omega. Now, of course, this integral depends on the path, but the point is that if you choose two different paths, then the difference between the integrals is the integral over the closed path. We first go from P1 to P by one path, and then we come back to P1 by other path. So we get a period, and any period, since the cohomology class of our omega lives in this lattice, any period is integer plus I integer. We quotient over integers plus I integers, so meaning that this integral up to this ambiguity is well defined, so we get a well-defined map to the torus, and all their zeros, since we live here and since even the relative cohomology is integer, all the zeros would be mapped to the same point of the torus. So we get a ramified cover over a torus where all ramifications are over the same point. So this torus is square tile. We glued it from a square. We can pull it back upstairs and we get square tiling upstairs. And so integer points, square tile surfaces are integer points in the strata, and counting them is basically equivalent to counting Мэйзура-Вича volume. Here I have a history of computation of Мэйзуra-Вича volume, and probably I will somehow, I already mentioned this, so probably I would scroll this and move this historical page. I just can know that this last years, there were plenty of activities. In particular, they were really breakthrough in proving all conjectures of Eskin and myself on asymptotics of Мэйзура-Вича volumes.
The calculation is a little bit less interesting than the ones that I now.
Sorry?
You may continue. It's just a side interruption.
I see. So it was not a question, neither question nor remark.
No.
Okay.
I believe.
And now, so now the details on the proof and on identification. So first in genus 0, every square-tiled surface defines a pair of transverse simple closed multicurves. So we get this bijection between pairs of simple closed multicurves and square-tiled surfaces. Bigons arising from intersection of transverse multicurves correspond to simple poles. So when I fix the number of bigons, I fix the number of corners with angle pi for my square-tiled surfaces. And counting all pairs of simple closed multicurves with at most 10 intersections is the same as counting the number of square-tiled surfaces, of genus G with p poles. So we know that it's asymptotic to this number, and this constant up to dimensional, simple-minded dimensional factor is just Мэйзура-Вича volume. So the previous slide was about Мэйзура-Вича volumes. They are computed, and there are plenty of things which are known about them, both in the case of an orientable case, which corresponds to abelian differentials, and non-orientable case, which corresponds to quadratic differentials. The main difference is that the powers of n are different. But so to compute meanders, we have to, so denominators are now Мэйзура-Вича volumes, and to compute meanders, we have to compute the C1 and C1 plus in orientable case. So for meanders, we have to compute one cylinder square-tiled surfaces. And as I mentioned, we have formula based, we meaning together with Delecrua, Gужар, and Zograf, we have formula through Witten-Conцевича correlators for them, which was presented last time. And in this particular case, when we have just one cylinder, or when horizontal curve is simple closed curve, there are only 1 and 2 correlators which are involved. And for 1 correlators, there is explicit formula. For 2 correlators, we proved excellent approximation. Now, for genus 0, there is an extra simplification because there is an explicit formula for Мэйзура-Вича volume. It's not recursive formula, it's given by formula. So, which is here, and actually it works for any stratum, and I need only for the principal stratum, and for the principal stratum, the formula is particularly simple. So it's just this. So you see there is power of pi, power of 2, and factor 2 pi. Looking at this formula, I cannot somehow cannot mention the following. So I remember attending a talk of Don Zagir where he suggested some nice combinatorial explicit answer for nice combinatorial formula, saying that, well, of course, this formula is given up to powers of pi, powers of 2, and factorials. So if you write formulas up to powers of pi, powers of 2, and factorials, this formula becomes sort of tautological. So lose any sense.
Yeah, but anyway, it can be 1, but not 0.
Yes. I should say that I'm so happy about this formula because if, for example, you use naively our formula based on Witten-Conцевича correlators, then it's a nightmare. even in genus 0, it's an enormous sum over enormous amount of stable graphs. And I should say that while in large genus, the entire volume sits down on very clearly identifiable collection of stable graphs, here, according to experiments, really enormous amount of stable graphs are involved. And it is still a mystery that, for me, that it somehow converged to such a simple formula. This mystery is partly demystified by recent work of Chen, Möller, Sauvaget, where they obtained formula for Мэйзура-Вича volumes through Hodge integrals and through intersection theory. And now,
but then there should be some expression for this. This is an expression for an enormous sum over labeled trees. Therefore, this enormous sum, it's a kind of a combinatorial identity, and what kind of identity is it?
We already our way to prove this value for the volume, which was obtained with J. Devathrey and Alex Eskin, it was through combinatorial identity, which had sort of crazy origin. So we had a formula for some dynamical object called sum of Lyapunov exponents, or rather, through Riemann-Roch theorem and so on, joined with Eskin and Concevichu. Now, in genus 0, the sum of Lyapunov exponents is 0 sort of by definition, they are known. Still, the expression for the sum of Lyapunov exponents is meaningful, and it involves, it's a polynomial in, rather rational function in volumes of the strata. And from the structure of the formula, it's clear that there is a unique solution for all these equalities. So we had to prove that the guess that this ansatz satisfies these identities, and it was sort of a strange combinatorial identity for certain expression of certain rational function and factorials, which was proved purely combinatorially, and it was quite a combinatorial exercise. Now, so this was initial proof. I did not even try to analyze their sum over all stable graph. Well, I decided not to. At the current stage, I didn't analyze the sum over stable graphs because at some point I suggested their diploma project to a master's student to check whether there are some privileged stable graphs which carry all the volume. He realized that not. And it seems like this is a problem for people working in probability. They really tackled their random spheres, random quadrangulations of spheres, and they have some technique on this. So it is sort of a project for a future project. I think that I will, to study these identities, I have to start by sort of series of discussions with them to understand what they can do. So they have some technique, and it would be stupid to ignore that there is already some developed technique for this problem.
Thanks.
I can give names if you wish of people who were working with the school of Jean-François Legal, but people are really in. Okay, so now I advance with my demystification. And now it really starts. So now I'm going inside the proofs, and I'm speaking about demystification. So the first part of the theorem, it's just, I'm happy with this, but it's not particularly useful for meanders. So probably since the time is going, I will skip it. But the second part of the theorem is really important. This is the key idea for the calculation of meanders. So the identity C11 over C1 equals C1 over C can be interpreted in terms of count of square tile surfaces in the following way. So we can count all square tile surfaces. We can count square tile surfaces which have single horizontal band of squares. So horizontally, you just glue squares in a long band one after another, and there are no other horizontal bands. Just all the surface is one single horizontal band. And now among them, there are even more special surfaces which have single horizontal band and single vertical band of squares. And that's exactly the square tile surfaces which correspond to when you consider all, you get all pairs of multicurves. Single horizontal band means that you have simple closed curve horizontally, and single horizontal band, single vertical band, it's single closed curve horizontally, single closed curve vertically. And the theorem says that the vertical and horizontal decomposition of their of square tile surfaces are uncorrelated. So if you take all square tile surfaces, and so what I'm saying is a consequence of slightly stronger theorem saying that horizontal and vertical foliations are uncorrelated. In particular, you can consider instead of those square tile surfaces which have single band of squares, you can consider those which have k different maximal horizontal cylinders. And the probability to get a surface which has k maximal horizontal cylinders out of all square tile surfaces is the same as probability to get a surface having k maximal horizontal cylinders after those which have j vertical maximal horizontal cylinders.
And
So
this is valid for each stratum, yeah?
This is not asymptotic. It's valid for each stratum, for abelian and for quadratic differentials, and it is valid even. Actually, it is valid even for more. It is to show off. It is valid for arithmetic and variant submanifolds. So I don't want to go into details, but their magic quant theorem of Eskin, Mirzahani, Mohammadi, and the specification of it by Simon Philippe proves that if you take any orbit of GL to R in any stratum, you take the closure of this orbit, you get nice invariant submanifold. Some of these invariant submanifolds are defined over Q, over rationals. So, and for them, the same result is true. And the reason is that basically that the coordinates in our stratum, let's stick up to the stratum. The coordinates in the stratum are these period coordinates. And period coordinates are cohomology with coefficients in z plus iz. We can fix real part and move along imaginary part. And actually what I'm saying is that they're completely independent, and real part sees everything about vertical decomposition and imaginary part sees everything about horizontal decomposition. So if you take, say, instead of lattice z plus iz, rational lattice with some small step, and inside your coordinates, like here in the picture, you fix real part and you change imaginary part, then all the points of this vertical fiber will have the same vertical decomposition. And this instantly apply, well, not instantly, with this observation is a key observation which implies this relation. So, the key idea of the proof is that we have these period coordinates, and changes of coordinates do not mix up real part and imaginary part. And when we're in a lattice, then real part knows about one decomposition and imaginary part knows about complementary decomposition, and that's why they're uncorrelated, and that's why we have this kind of funny result. So this is just the repetition of the strategy that we associate to a multi-curve square tile surface, and then use this relation, and then we use the volume. This is again the general philosophy, which I think that I can now, which is applicable to any genera, to all genera and so on. So to finish, let me say several more words about orientable case and how we count one cylinder square tile surfaces in orientable case. It's somehow related to permutations. So first is that there is this formula for the asymptotic formula for the volume of the Мэйзура-Вича volumes of strata of abelian differentials, which is proved by Agarwal, by Chen, Müller, Zagir. So this is known. Now, how do we, so this is to count denominator, how do we count one cylinder square tile surfaces? So in this particular case, when we work with abelian differentials or with oriented meanders, when we have a single band of squares, then basically it can be encoded by a permutation. We can number the squares 1, 2, 3, 4, etc. in the band. And the horizontal permutation remembers who is the right neighbor. And in this particular case, the right neighbor is just right neighbor of 1 is square number 2, right neighbor of square number 2 is square number 3, etc. up to n, and the right neighbor of n is 1. So it's the horizontal permutation is just a long cycle. Now, the vertical permutation is some permutation. And the condition that we belong to certain stratum is the condition that the commutator of two permutations belongs to, has given decomposition. Now, so we want given decomposition into cycles, meaning that given decomposition into interesting cycles. So when we have a complicated square tile surface, then the commutator of horizontal permutation, which tells who is the right neighbor, and vertical permutation, which tells who is the top neighbor, we get something interesting only when we go around the zero. When we take a regular square where everything is completely flat, we go to the right, top, left, bottom, and we come back to the same square as before. So when we live in a fixed stratum, then a commutator of such permutation for a complicated square tile surface having plenty of squares, so it has several interesting cycles, which is one and the same, and their lengths are one and the same, and they're basically the degrees of zeros. So for the principal stratum, for example, we'll have cycles of length 2, and we have enormous amount of trivial cycles of length 1. So counting square tile surfaces is equivalent to counting counting square tile surfaces with this single horizontal band is the same as counting pairs of permutations like this. And we can easily pass to counting permutations having given commutator to pairs of just long cycles, such that the product of one long cycle times the other long cycle is the product of cycles of given length completed with enormous amount of cycles of length 1. So this problem can be treated through Frobenius formula, and you get explicit answer like this, which is sort of not particularly practical because in general, because there are these characters, but there are two simplifications. So if your cycles are simple, then you can compute the character explicitly. And also when the number d is large, then you can use the formula of Zagier, which bounds this C1 between these two fractions. And this is for any d and for any stratum, for any collection of zeros. And when the stratum is particularly simple, for example, the stratum is principal, then you can compute the character and you get explicit answer. And when the stratum is minimal, you can also compute the character and you get explicit answer. And I think that I told everything which I wanted to tell. I would be happy to.
Thanks a lot, Anton. Are there any questions, comments? Максим.
Антон, я что-то пропустил, в какой момент пропала информация о коммутаторе? Вот здесь написано n cycle times n cycle is product of cycles of lengths, given lengths, а информация о коммутаторе все время говорил, а потом вдруг раз, и она исчезла. В какой момент она исчезла?
Just a second, can I double check? Да, я могу переключиться на русский.
Давай я еще предварительный вопрос задам. Какая связь между n большое и d маленькая?
Значит, я вернусь вот к этому слайду. У нас мы решаем такую задачу в терминах перестановок. Значит, у нас есть исходный геометрический объект, это поверхность в клеточку, которая склеена из одной единственной горизонтальной полоски, в которой все клеточки выстроены одна с другой. По горизонтали комбинаторика тривиальна. Все клетки идут одна за другой, мы их все увидим. Вертикально это нечто более хитрое. Это какая-то...
Верхние стороны и нижние стороны как попарно склеены, да?
Как-то попарно склеены некой перестановкой. Теперь, если мы возьмем любую перестановку, мы получим какую-то поверхность в клеточку, вот, у которой горизонтально единственная полоска из клеток. Если мы хотим попасть в нужный страт, то на эту пару перестановок нужно наложить такое условие. Значит, когда мы идем, начиная от какой-то клеточки, направо, потом вверх, потом налево, потом вниз, если мы обошли обычную регулярную вершину, в которой подклеены 4 клеточки, но мы и вернулись назад. То есть для таких элементов коммутатор тривиальный. Мы пришли назад. А вот когда наша клеточка подцеплена, когда ее угол, нужный угол, примыкает к конической особенности, то мы идем направо, вверх, налево, назад. Но мы не сделали полный оборот вокруг конической особенности. Мы пришли в другую клетку. И мы должны продолжить это. И коммутатор, примененный к такому элементу, он даст некоторый цикл какой-то длины. Длина этого цикла – это в точности порядок нуля плюс 1. Так что вот пока в этой формулировке мы переформулировали задачу так. Значит, у нас есть некоторое число циклов, которые отвечают за порядке нулей. Скажем, если у нас старший страт и у нас 2g минус 2 простых нуля, то у нас 2g минус 2 цикла длины 2, которые мы дополняем, так как поверхность клеточку содержит огромное количество клеточек, мы дополняем их огромным количеством циклов длины 1. И теперь мы спрашиваем, а сколько есть перестановок длины не больше, чем n, у которых коммутатор – это 2g минус 2 цикла длины 2, дополненные нужным количеством циклов длины 1. Если одна перестановка – это длинный цикл, а вторая, ну вот уж какая получится. Значит, когда мы пишем коммутатор с длинным циклом, то мы можем взять тройку элементов, вот эту вот хитрая перестановка умножить на длинный цикл, умножить на хитрая перестановка в минус 1, это тоже длинный цикл. И мы просто переписываем, вот теперь я перехожу к этому слайду, мы переписываем предыдущую формулу, вместо того, чтобы написать коммутатор, длинный цикл с какой-то хитрой перестановкой, мы вот длинный цикл запоминаем, а сопряжение длинного цикла в минус 1 вот этой хитрой перестановкой мы просто прячем в новый длинный цикл. И переформулируем задачу так. Сколько есть длинных циклов, таких, что их произведение имеет следующее разбиение на непересекающиеся циклы. У нас есть сколько-то циклов фиксированной длины, которые мы запоминаем раз и навсегда, и мы их дополняем огромным количеством циклов длины 1, чтобы общая длина перестановки стала равна n. Это ответ на
понятно.
вопрос.
А это самое, один цикл можно, длинный цикл получить, из другого можно получить сопряжением неоднозначно, но
Да.
там
Да,
простой
да.
множитель,
Это
который всегда учитывается.
Точности. Этот фактор неоднозначности, он абсолютно банальный и всегда один и тот же. Так что это банальная переформировка. А вот эта задача, это уже в чистом виде теорема Фробениуса.
Ну, это нет, это задача, которая это мы знаем. Теорема Фробениуса – это одна из вещей, но в принципе перечисление таких вещей это самое перечисление карт, гиперкарты, это там и топологическая рекурсия, и матричные интегралы, про это мы все знаем.
Да, без сомнения. А вот эта формула, ну, я думаю, что там вы ее узнаете, потому что это Зогир в какой-то момент переписал формулу Харра-Зогира вот в терминах вот этой задачи. Сколько есть асимптотика числа пар длинных циклов, которые дают такое разбиение. У него формула для разбиения, когда все циклы указаны. Но если посмотреть внимательно на его формулу, это, собственно, единственный вклад наш. Если посмотреть внимательно на его формулу, то она не зависит от числа циклов длины 1. И поэтому получается просто немедленное решение задачи, которую мы решаем, и можно использовать его оценки, которые вот здесь вот записаны. Ну а формула, честная формула, это честная формула через характеры, когда представление особенно простое, а именно когда либо в старшем страте у нас все циклы 2,
либо столбик, либо...
Да. Здесь к счастью, характеры выписываются явные, поэтому получается явная формула.
Но, Антон, тем не менее, я все-таки еще раз хочу сказать, что разложение по характерам – это, как бы сказать, первое, что приходит в голову, но с тех пор там в этой науке очень много всего добавилось, связанное с топологической рекурсией и прочим.
Верю. И это одно, да, и ты, может быть, в другой форме, ты мне это уже один раз говорил, а я со стыдом должен признать, что я это забыл. И в каком-то смысле, так как результаты получились уже вполне удовлетворительными для народного хозяйства, да, мы на этом остановились. Но ты прав, на это можно посмотреть без прямой прагматической выгоды для народного хозяйства. Это может быть забавно, да.
Ну вот, по крайней мере, вот то, что написано наверху, это, как сказать, вызов для меня. Я могу попытаться, что...
Если с левой стороны можно брать что-нибудь более интересное, чем длинный цикл, то это становится очень интересной задачей, потому что это подсчет вклада поверхностей в клеточку из не только одноцилиндровых, а там 2, 3, 4 цилиндров. И мне лично это интересно, потому что, ну, во-первых, у нас есть гипотеза о том, что асимптотически это распределение устроено как распределение случайных перестановок. Для квадратичных результатов мы теорему доказали, а для абелевых, для которых, казалось бы, все проще, доказать не можем. Это одна вещь. А вторая вещь...
Ну, вот, значит, да, Антон, сейчас я так, еще раз я хочу тогда подытожить. Значит, ты в исходной задаче ты интересовался перечислением пар перестановок, коммутатор которых дает заданный циклический тип. Но вот про эту пару перестановок, значит, тут можно разные вещи спрашивать. Либо ты саму цикловую структуру их либо фиксируешь, хотя бы одной из них, и тогда, если ты оба цикловых типа фиксируешь, то я ничего не могу сказать. Но ты сейчас сказал более простую задачу, когда ты у одной перестановки фиксируешь цикловой тип, а у второй перестановки ты берешь произвольные, все смешиваешь вместе. И тогда можно вот при помощи сопряжения у нас получается все равно, что перечислять пары перестановок двух одинаковых циклических типов, так что они в произведении дают то, что нужно.
Да.
Вот, значит, если ты на вторую перестановку не накладываешь никаких циклических ограничений, то тогда эта задача сводится к тем задачам, которые, значит, нам уже известны ответы.
Сейчас, почему это двух одинаковых циклических типов? Это я не понял.
Потому что вторая получает с первой сопряжением при помощи. Значит, вот то, что он говорил, Антон, что вместо того, чтобы говорить про коммутатор, можно говорить, что у нас есть одна и сопряжение второй.
Угу.
Одна и она же сопряженная второй.
Да, понятно.
Коммутатор написан как А, Б, А в минус первый, Б в минус первый. И ты его теперь разделяешь на А.
Да, понятно, да.
Миш, а формула Шапира-Вайнштейна здесь не годится для чисел Гурвица многочленов произвольного рода? Полиномиальных. Ну, если есть цикл полной длины.
Ну вот да, я тоже думал, вроде годится, да.
Должна. Хорошо. Какие еще вопросы, комментарии?
У меня есть не вопрос, а пожелание. Антон, ты не можешь слайды прислать, а то я что-то здесь какую-то ерунду сделал. Ой, сейчас я, во-первых, эту запись